Hello class, welcome to the lecture number 3 of Input-Output Organization. In the previous class, we were discussing about asynchronous data transfer and how the strobe method helps us to establish the asynchronous data transfer. We saw that the strobe gives us a way of informing the source or the destination about the presence of fresh piece of data on the data bus. If the strobe is initiated from the source side, what it does is the source puts the fresh piece of data on the data transfer on the data bus and sends a strobe to the destination unit. If it is initiated from the destination side, the destination gives a strobe to the source side, indicating that it is now ready to accept the data, and in response the source side will put a fresh piece of data on the data bus. But the disadvantage give us any way of acknowledgement. See, basically, if it is a source initiated strobe, the source unit has put some data on the data bus and it has initiated the strobe, but it has no way of knowing whether the destination unit has actually read the data. Similarly, if it is a destination initiated strobe, the destination unit indicates to the source unit that yes, I am ready to accept the data, and then it expects the source unit to have put the data on the data bus, but it does not have any way of actually knowing whether the source unit has put fresh piece of data on the data bus or not. Now this may cause a problem. Say if the destination unit has initiated a strobe, but the source unit has not yet put in some data on the fresh piece of data on the data bus. Now the destination unit, when it reads the data from the data bus, as we have already talked about, that the data bus is never empty, so there is no way of ascertaining that the data on the data bus is a fresh piece of data or is it a previous data. Now one way of overcoming this problem is to introduce certain acknowledgements. This is what we do in the handshake method. The handshake method essentially gives us a way of acknowledging the signal that has been initiated by the either the source unit or the destination unit. Let's see it. Now once again, the handshake can also be initiated either from the source side or the destination side. Let's first talk about the source initiated transfer using handshake. You can see we have the source unit and we have the destination unit. The data bus is still traveling from the source unit to the destination unit. Now, instead of the strobe, we have a data valid signal that is coming from the source unit to the destination unit. And in addition, we have a specific signal that is a data accepted signal that is going from the destination unit to the source unit. Now let us see how things happen over there. If you see this sequence of events, this will tell you the how the process is going on. Now it starts with the initially what happens is, if you see this timing diagram, initially there is no data on the data bus. The data valid signal is reset. The data accepted signal is, let us say it is at 0. Now the process starts with the source unit putting some data on the data bus, and as it does, as it puts the data on the data bus, it enables the data valid signal. This indicates to the destination that a fresh piece of data has been placed on the data bus. Let me repeat. The source unit puts some data on the data bus, and at the same time it sets the data valid signal indicating the destination unit that a fresh piece of data has been put on the data bus. Now when the destination unit receives the data valid signal, when the destination unit receives the data valid signal, what it does, it accepts the data from the data bus, and after reading of the data from the data bus, what it does, it sets the data accepted signal. Now this is a sort of acknowledgement to the source unit that yes, I have seen your signal and I have read the data. So it accepts the data from the data bus and it enables data accepted. Now, once it enables the data accepted signal, this data accepted signal is sent from the destination unit to the source unit. Now when it reaches the source unit, now the source unit comes to know that yes, the data has been read by the destination unit. Now what the source unit does, once it sees that the data has been read by the destination unit, it disables the data valid signal. It disables the data valid signal. Let me reiterate once again, there is no way of removing the data from the data bus, but this disabling of the data valid signal indicates that the data that is there on the data bus is no longer a valid piece of data. Once the source unit disables the data valid signal, indicating that the data is no longer valid, when this signal reaches destination unit, what the destination unit does, it disables its data accepted signal, right? That means it is now ready to accept a fresh piece of data whenever the source unit will tell it. And if you can see, this initial state and the final state are both same. So source initiated transfer using handshake is similar to your source initiated strobe, but with an additional acknowledgement signal coming from the destination unit to the source unit. If we talk about destination initiated transfer using handshake, again you see we have a source unit, we have a destination unit, we again have a data bus, we have a data valid signal, but now we have a different signal which is the ready for data signal. Once again, look at the sequence of events. If you see, now the process starts with the destination unit. Once the destination unit is ready to accept the data, once it is ready, it can start accepting the data from the source unit. It indicates this to the source unit by sending the ready for data signal. So this is the first task. So its process starts with the destination unit enabling the ready for data signal. Once the source unit sees this ready for data signal, it puts the data on the data bus and enables the data valid signal, telling the destination unit that now the data that is there on the data bus is a fresh piece of data. So the source unit places the data on the data bus and enables the data valid signal. Once it sees this, once the destination unit gets the data valid signal, it knows that the fresh piece of data has been placed on the data bus. What it does, it reads the data from the data bus, and to indicate to the source unit that it has accepted or it has read the data from the data bus, it disables the ready for data signal. Now this disabling of ready for data signal does the exactly same task which was done by the data accepted signal previously. Now this disabling of ready for data signal indicates to the source unit that the destination unit has read the data, and in response the source unit disables the data valid signal, thereby invalidating the data on the data bus and bringing the entire process to the initial state where the destination unit is once again ready to accept the next data after sending a signal to the source unit. Now we have talked about asynchronous mode. Now, if you remember when we talked about the classifications or the categorizations, one more categorization was serial versus parallel categorization. Now, we may have a serial input output or a parallel input output. In case of parallel input output, if I have a n-bit data to be transferred, say it can be an 8-bit data, if it is an ASCII data, it can be a 16-bit data, it can be a 32-bit data, whatever it is. So in parallel data transmission, if I let us say take the example of 8-bit data, then these 8 bits of data travel on 8 lines. So the data bus needs to have an 8-bit line to carry the data in parallel. So in parallel data transmission, each bit of the message has its own specific line over which it is traveling. Whereas in case of serial data, we just have one line, or let us say we can have two lines over which the entire data is transferred bit by bit. So as you can see, parallel data transfer would obviously be faster because it is transmitting all the lines, it is transferring all the bits at the same time. But at the same time, though it is fast, but it is also expensive. Why? Because it requires many wires. Whereas serial transfer is slow, but it is less expensive. So for this reason, parallel transmission is normally used for shorter distances and serial transmission is used for longer distances. Now, as I discussed earlier, those four types of categorizations of input and output, they were independent of each other. So you could have a parallel synchronous IO, parallel asynchronous IO, or serial asynchronous IO, or serial synchronous IO. Let's talk about serial synchronous versus serial asynchronous. In synchronous transmission, see what happens is that the source unit and the destination unit, if they are communicating synchronously, they have to share a common clock frequency. Moreover, bits need to be transferred continuously from the source to the destination at the transfer rate that is dictated by the clock pulse. This is necessary so as to maintain the synchronization. Say, let us say the two units are not close to each other, then we would have to send the synchronization signals continuously or repeat periodically between the two units to keep their clocks in sync. Whereas in case of asynchronous transmission, there is no continuous transmission of data. In case of asynchronous transmission, the data is transferred only when it is available, and the lines will remain idle. The lines will remain at a stationary state, at a stable state, or at an idle state when there is no data to be transmitted. Right? Now, if we talk about asynchronous serial transfer, as I just explained, in case of asynchronous serial transfer, the data bits are not being transmitted continuously, but they are only transmitted whenever there is a piece of data that has to be sent from the source unit to the destination unit. So we may have asynchronous or synchronous serial parallel transfer. Now, asynchronous serial transfer is most important. So what we do is, how do we tell? See, as I've already told you, the bus or the line or the signal line can never be empty. It has to be maintained at either a zero state or a one state. So how do I tell my receiver when does the character start and when does the character end? So what happens is, each and every character, obviously the characters are made up of bits. So each character bits are enclosed within the source bits and the start bit and the end bits. So by default, the line is maintained at a one state. Now listen to this carefully. By default, when there is no data being transmitted from the source to the destination, the line is maintained at a one state. This one state is the idle state. Now, whenever the source wants to send some data to the destination, it will start with sending a start bit, then it will send the character bits, and it will finish it off by using the stop bits. Now, what will be the start bit and what will be the stop bit? These are agreed previously between the source and the destination. But in general, the start bit is a single zero. It is always a single zero, right? And the stop bits are usually one or two one bits, right? So a character can be detected. So how does the source send the data? It has, see this example, it has this data 11000101. This is the data that is to be sent. These are the character bits. So for sending that, it will first add a start bit, which is obviously a 0, and it will add two stop bits, which are two ones. So this 8 bits plus 1 9 plus 2 11 bits will be sent on the line. So this one character, which was initially of 8 bits, is now made up of 11 bits by adding the start bit and the stop bits, and these 11 bits are transmitted to the destination unit. Now the character can be received by the receiver by knowing these four rules. Number one, when the data is not being sent, the line is kept at the one state. One state, as I've already told you, is the idle state. The initiation of the character transmission is detected by a start bit, which is always a 0. So my line is at an idle state, that is a one state, and as soon as I get a 0, I know that a new character is starting. It is followed by the number of characters which are making up the character bits. The number of bits that make up a character has to be finalized between the source and the destination beforehand. Then they are followed by two 1 bits which make up the stop bits. Important point is the transfer rate and the number of information bits, number of character bits which make up one character, must be agreed upon between the source and the destination beforehand. Let me repeat, the transfer rate of the bits and the number of information bits to expect, these are two very important parameters. Why? Because the transfer rate of the bits will tell the receiver what is the length of a single bit. What if, let us take an extreme example, what if the entire piece of data is made up of zeros? So how does the receiver know where the start bit ends and where the data begins? So that can be known if the receiver knows the transfer rate of the bits. Let's put it all together. Now the diagram that you see is an asynchronous communication interface. Now see this diagram carefully. This is an asynchronous communication interface. On this side we have the CPU, on this side I have the device. Now we have the bidirectional data bus connected to the bus buffers. I have the timing and control logic, which has certain inputs from the CPU side, means chip select, register select, read and write. On the device side, I have the transmitter register, control register, status register and receiver register. These, as you know, are part of the interface. And then I have the shift register, transmission control and clock, receiver control and clock, and shift register. Now this table over here is telling me how the registers are selected, right? Let's go into details. Now this asynchronous interface, the bits in the status register, this status register that you see over here. Now these bits in the status register are used for input and output flags. There are essentially two types of flags which are used mostly. One is the flag that indicates that the transmitter register is empty, and the second flag is used to check whether the receiver register is full. Why? Because a new character cannot be sent to the transmitter if it is not empty. Similarly, a data cannot be read from the receiver if the receiver register is not full. Now this chip select input, this is used for selecting this particular interface. The chip select and the read write. See, there are four registers over here: transmitter register, control register, status register and receiver registers. If you see carefully, two of the registers are read only and two of the registers are write only. So we use this register select, chip select, read and write, these four signals to select a particular register, as you can see in this table. So the CPU selects a particular register with which it wants to communicate by selecting the CS, RS and read and write lines. Let's see the operation. The interface is initialized for a particular mode of transfer by means of a control byte. Now the control byte that the CPU sends is essentially made up of the value of the chip select, the value of the register select and the value of the read and write. Now what happens is the transmitter register. See, this device is an asynchronous, serial asynchronous interface. What does it mean? It means that whatever data is being transmitted from here is being transmitted serially. Similarly, whatever data is being received from here is being received serially. But the data transfer between the CPU and the interface, it happens in parallel. So let's go into detail. So you can see over here the transmitter register accepts a piece of data or a byte of data from the CPU through the bus buffer, through the bus. This is coming here. The data is coming from the CPU to the transmitter register in parallel. Then it is transferred to the shift register and it is transmitted. The data, the receiver receives the data, one byte of information or one character of information serially, then transmits it in parallel to the receiver register, which then transmits it to the CPU over the bus. Let's talk about these two operations one by one. Let us see how does this system works as a transmitter. Now what happens is the CPU first reads the status register in order to ascertain whether the transmitter register is empty or not. Now this status register, as I mentioned earlier, has two important flags. One is the flag that tells me whether the transmitter register is empty or not, and the second is the flag that tells me whether the receiver register is full or not. So while transmitting, the CPU first checks whether the transmitter register is empty or not. If it is empty, listen to this carefully. If it is empty, the CPU transmits one character of information to the transmitter register. Now it is sending 8 bits of information in parallel to the transmitter register. And at the same time, the status register clears the flag that indicate that the transmitter register is no longer empty, it is now full. Now here in this transmitter register, the start and stop bits are added. The first bit is set to 0 and then the character bits, and finally we add 1 or 2 stop bits as per the system. Now this 11 bits are sent in parallel to the shift register, from where it is transmitted in series to the outside. When the system is acting as a receiver, what happens is the line by default is in the 1 state. As soon as the shift register receives a 0, it knows that it is now receiving a particular character. Then it starts accepting the data. It accepts the 8 character bits and the 2 stop bits. So it receives the 11 bits in total. Now this shift register strips the start and the stop bits and sends the 8 character bits to the receiver register in parallel, and from here, from the receiver register, the bits are transferred to the bus buffer and to the CPU. This again operation is carried out by first checking the status register, continuously checking the status register whether the receiver register is full or not, because it is no use the CPU reading the data from the receiver register until unless it is full, until unless it has received the full number of characters. So this is how this particular asynchronous interface works as both transmitter as well as the receiver. So this we have till now talked about the serial versus parallel communication. We have talked about the asynchronous versus serial communication. We have talked about the memory mapped versus isolated communication. In the next class, we will talk about one of the more important categorizations, that is the program controlled IO versus the interrupt IO versus the DMA. Right? Thank you.